Okay, so today we're going to talk about mass spectrometer and how they work. So a mass spectrometer basically has four parts, four basic sections that you could say. The first one is going to be called the is called the ionization chamber, where the ionization happens. I'm going to get into details later on. The second one is called the acceleration section. The third one is deflection. The fourth one is detection. So the ionization is done by an electron gun. The acceleration is going to be done using electric potential, or you could say electric plates. The deflection is done using a magnetic field. This is the crucial part of a mass spectrometer. I'm going to get into that later on. And then the detection is done using computers and detectors. Just call it detectors. Okay, so this is what a typical mass spectrometer looks like. So you have a probe where you would insert your sample. The important part is the sample needs to be a gas. So if you have your sample is if your sample is a solid or a liquid, you need to make sure that you make it a gas. So the sample enters it through the probe, and this is where the electron guns are, and they ionize your sample. So you can see in this picture that the sample is in black. So that represents that it is not ionized yet. So as it goes through these high energy electrons from the electron gun, your sample gets ionized. I'm going to go into that later on. So the the red bits here are the ionized sample. So the reason you ionize them is because you want them to accelerate, right, towards the detector. The detector is here. So first you make them positively charged. You make your sample positively charged so that you can use the electric plates here. These are where the electric plates are. These are our accelerator plates. So these electric plates are negatively charged, right? Are negatively charged. So your sample is now positively charged, so it gets attracted towards the electric plates, and there's a little slit, a little opening. So some of the sample are going to go through the plates. And then next what happens is you have a giant electromagnet here. So that's going to uh, exert a magnetic field. So depending on that, depending on the mass of your sample, it's going to get deflected. And there are small tiny slits here, right? Small tiny openings. So only the dead on straight samples are going to go through that. And then here's your detector. So you detect the sample. So how does it really work? So it might be a little bit difficult to comprehend because we're talking about moles and a machine that you've never seen in your life or heard of. So you might not be able to connect to it. So just so that you can connect to it, so I'm going to talk about, I'm going to give you a real life example, right? At least I'm going to try. So imagine, imagine that you have a truck, let the square be a truck, and you have a car, let this square be a car, and then you have a bicycle, right? A bicycle. So definitely the truck weighs more, right? And then the car is in the middle, and the lightest of the three is a bicycle. Nice. So imagine this is a highway, and there is an exit on the highway. This is the exit on the highway. So this is the highway, and in this exit, you are standing here. This is you. But you're blindfolded. You are blindfolded. and there's a, let's say there's a bell here. There is a bell here. So I'm not going to be good at drawing a bell, but imagine this is a bell. So the idea is you might have a truck coming down this road, and you would need a certain force to turn the truck. Say, for example, just for argument's sake, let's just say that the force is just say 20 Newton. You need to apply 20 Newtons of force to make this perfect exit. And then the truck would come and hit the bell, and when you hit the bell, when the truck would hit the bell, you can hear it and you'd know that, okay. And say, for example, you have a device in your hand, okay? So that device, like you can choose the turning force that's going to be applied to whatever is coming down this road, okay? So you know that you need, say, 20 newtons of force to turn a truck. You need 10 newtons of force to turn a car, and you need, I don't know, maybe 5. So you need 5 newtons of force to turn a bicycle. So you know those, like you know these informations. You have these informations, and you control the turning force by some remote control or whatever. So if a truck was coming along, you don't know what is coming down the road, right? You have no idea. You're blindfolded. So let's imagine that. Okay. So let's imagine a truck is coming down the road and you have no idea. So what you do is you apply 5 newtons of force. So what happens is the truck doesn't get enough turning force and it never makes it to the exit. Right? It never makes it to the exit. So it hits the bank here. Okay. Then the truck goes again, and then you apply, say, 10 newtons of force. Now, so this is the 5 Newton one. So now you apply 10 newtons of force, and you still don't make it, barely, we're almost there. So this is, say, 10 newtons of force. But when you apply exactly 20 newtons of force, the truck goes into the truck makes the exit and hits the bell, and you can hear it now. So now you can connect the dots that I have applied 20 newtons of force and then somebody came into the exit. So it must be the truck. So that way you can figure out that it was the heavier object out of the 3. So now let's say a car was coming along, right? So let's say a car was coming along. I keep erasing this bit of the exit. Okay, so now this is the car, and you apply 5 newtons of force. It doesn't make it. It hits the bank. Then you apply, the car again comes around, and then you apply 10 newtons of force, and it goes all the way, and it hits the bell. You hear it. So just to be sure, you make the car go around again, and this time you apply 20 newtons of force. What's going to happen? Well, the car is going to make a sharp turn and hit this wall. So this is for 20 newtons. Either way, it doesn't make it. It only makes the exit if you apply 10 newtons of force. So that way, you can figure out the mass of that object, and that object was a car, right? So that is exactly how an ionization, like a mass spectrometer works. So you have samples, and you don't know their masses. So what you do is you ionize them so they become positively charged. And the reason you want to ionize them is because you want to accelerate them. So the way you would do that is using an electric plate, which is negatively charged. So this is the acceleration. It gets momentum. Your sample gets momentum. This is this force, the force of the truck or the car or the bicycle that was going along. And then the deflection force, magnetic field, this is what you were doing here, controlling with the remote. And when it makes it, the bell is the detector. When it hits there, you know that, well, it made it. So its mass must have been this. So for the car, in the case of the car, so what you're going to see is when I applied 10 newtons of force, it hit the bell, it was detected. So that thing must be a car. So that's how you can use a mass spectrometer to figure out the mass of an unknown sample. So in the next part of this video, we're going to see some real life data and figure out the masses of samples. So I'd like to add one more thing here. So the manufacturers of mass spectrometer, what they would do is they would insert a known mass of sample into the mass spectrometer, and they would figure out that at what strength of the magnetic field the sample makes it just into the detector. Because if the magnetic field is a little bit weaker, it wouldn't make it. It wouldn't make the turn. It would hit the walls here. Okay, let me just point it out here. If the mass is too heavy for that particular magnetic field, what would happen is this guy wouldn't make it. It would hit the wall here. If it is too strong, it would make the turn too sharp and not make it. Just at the perfect amount of the magnetic field strength, the sample will make it through the slits and into the detector. So what's going to happen is in a modern mass spectrometer, the magnetic field strength, right? The magnetic field strength is going to go from 0% all the way to 100%. And then throughout this range, if you have only one sample, then you would detect those masses. There's something called fragmentation, which I'm going to come later on, not now. Fragmentation. We're going to cover it in probably the next videos, but not now. Don't worry about that now. So what the scientists would do is, in this example, you were told that if you apply 20 newtons of force and it makes it through the exit, it's a truck. If you apply 10 newtons of force and it makes it through the exit, it's a car. If you apply 5 newtons, it's a bicycle. So you were told this information, right? So the mass spectrometer, the detector, needs to know this information. So the manufacturers, what they're going to do is they are going to have the magnetic field and the detector work together in unison. So whenever the detector is going to detect a sample, right away it's going to talk to the magnetic field. Hey, what was the strength of the magnetic field? And say the magnetic field would say that, oh, my strength was around 55%. So what the detector would do is it would go back into its data booklet, right? Into its data book that was stored in the computer by the manufacturer. So it would go there and would figure out, hey, what sort of masses should be detectable at 55% of the magnetic field strength. And that way the detector is going to say, okay, so your sample's mass is, say, I don't know, maybe 200 grams, right? It's going to give you a mass by charge. So that's a little bit complicated, but for this moment, just imagine that you would know the molar mass of your compound, grams per mole. Let's just say that at this point. So that's how it works, basically.